Okay, we are here. Start. Thanks for joining, TJ, and let's see what Yaorong has to say. But one moment, TJ, can you confirm, yes, that you hear us?
Yes, I can hear you guys.
Perfect. Yeah, go ahead, Yaorong. It's definitely good recording on this.
Hi everyone. Today I will give a talk on the normalization techniques. This kind of it's more like a review or survey paper published in 2023. So there are a lot of details. Actually, I think all of the things in the paper you should know, or at least heard of them, or you can get the idea. But why you can talk of this paper here is when I'm looking at this one, I feel that okay, some of the normalization things I can apply here. Because when we're training a neural networks, we just assume that we need back normal, the layer norms out there. But why did you put there? Sometimes, well, personally for me, I sometimes I omit all this detail. So I'll give a quick review give a review of this. It will cover a lot of details, and I haven't never have so many notes for presentation like this time. So, but just we can discuss any moment because it's I just kind of summarize all the information. It's a very basic stuff, and normalizations are used for almost all the deep learning areas like computer vision, LM, speed and audio processing. And I will go through the three-part motivations and of how the normalization thing came out, why people use it, and review some normalization methods like back norm, layer norm stuff, and then some what they call the analysis of normalization, why this normalization included in this precise helped with the training precise. Definition. We know definition. I just copy paste. This is not my words. Everything is copy paste. So the normalization is we would generally say is like the minus mean divided by the standard deviation we have. It's more like won't have a very large variety or range of the data set. And I will not go through the definition, but in this paper, they kind of make normalization. When they say normalization, it's more like a general thing. So the process can be widening or zero means or standardized, and they cannot.
Yeah, but this is just standardization, right?
Yes.
This is one specific form of normalization. You can normalize it many different ways.
Yes. I copy paste there because I like their images, but not the comments, but still clear there. So I will start motivation from firstly from input. We know that when we try and train a neural network, we have the data to be normalized. Like when we do analysis on fMRI, we have different kind of normalization. This is what I learned when we can just general normalization or there has intensity normalization. So we perform differently. And so how do you get this idea? So they want to improve the effects of the learning precise. Like for unparametrical models like KNN, we know that it's a clustering method. When there's outliers very far away from it, when they evaluate the distance, so the large dissimilarity or dissimilarity will dominate the evaluation precise. So when trying to do normalization of the original data after zero century and normalize, it will be like in a smaller range. So it will be more stable, or I think it's just more stable, and that's it. And also, it can improve the optimization efficiency for a parametric model, like when you're training machine learning model, deep learning models. So when you update it, it can improve the optimization efficiency. So we see we most generally we do a gradient descent is when we optimize the parameter, we'll give a learning rate of that. But we can see for this two one with and without normalization, if this happens, we start training on this point. So because we're based on finding the maximum grading direction, we're trying to optimization based on the directions. But if you do not have a evenly separated contour line, like this one's the left. So when you optimize it, it will have a zigzag things. So this will make the training precise unstable and convert very slow. But if you have this one, the grading direction will directly point to the global minimum. This is what we want it to have. This is one of the motivation. And the second one is motivation by the curvature, which is related to the Hansen matrix. If you don't know Hansen matrix, the second order derivative of the is a second order derivative matrix, which is square and symmetric. So there's some information that people have research found that the optimum learning rate is equals to 1 over the maximum eigenvalue of the Hansen matrix. Okay, forget about mention about the curvature. So what curvature means is that when you have a curve, the larger the curvature is, it's more flat or smooth of the curve. So when you train the model, it will be optimized more converged and smoothly. But if you have a low curvature, like you have very sharp slope, so if you do not decide a good learning rate, it will sharply drop down to some maybe local minima or what is the global optimization part. So this is how people getting this idea really to the Hansen matrix. And if you're setting the learning rate too large, it will get diverged problem. And they also, for the condition number here, define as the maximum eigenvalue of the Hansen matrix divided by the minimum, so that they want the Hansen matrix eigenspace to be not that spread out, but to be more evenly separated. This is a motivation of the optimization part. And another motivation is about the activation. So here's the idea. When you're training a neural network, generally it will be deeper and it has a lot of layers. So consider each of the layer or specific neurons is just a linear precise. But when you combine all of them together, it will be more complex or more become nonlinear. But when you're optimizing each of the parameters of first or second or all the layers, they optimize together. This will cause more complex problems. So when we're trying to optimize each of the parameters through them, we don't want we hope we hope of the optimization to be stable, or we don't want any of the layers to be dominate the whole optimization process. This is how I think how the idea comes from for the normalization layer. If you have the layer to be each of the layer to be normalized and make it the training more stable, and optimization won't explode or vanish. Okay, yeah, this is a layer. So they get the idea of the layer by structure, and I think batch norm is also kind of related to this idea. Oh no, batch norm.
Well, batch norm is applied after each layer's activation.
Yeah, yes.
But across the samples in the batch.
Yes. And this is the motivation of the activation. And another thing is people, when we're training a neural network, people prefer to make the training well-conditioned landscape. How that this means? They want the neural network training to maintain a good optimization geometry shape. What I'm understanding is that people prefer to have this one instead of this one. This is what they want, the well-conditioned landscape. And they gave two definitions, two covariance. One is a covariance of input, the sigma x, and the second one is covariance of the gradient. Based on this, they have two criteria. They want the statistics of the layer input and the output gradient across different layer are equal. And also they want the two sigma to be bound condition. What the bound condition means, they want the um, maximum eigenvalue and the minimum eigenvalue to have a small ratio. So people trying to solve this by doing some initialization techniques. Like generally we set the initialization to be identity. There's some generally some normal, some default design, but people also have a different kind of initialization method, which can depends on what kind of and for initialization itself, it's just works at the beginning of the work. During the training, especially, you have a more complex model. The gradients will be affected significantly different. So in that condition, normalization layer will necessary to make the connection between layer to be stable and won't explode or vanish. Any questions for me? Next part, I will give a review of some normalization methods. So still based on three parts, normalization activations. So it's more general usage of normalization. You probably will see most of them. And then it's normalizing weights. This thing happens on the training of the how you do some tricks or concentrate on the weights. This happens not only in deep learning models and also many machine learning models. And then the normalizing gradients, I will just deliver information of that part. I will not talk too much on that. And let's talk first about the population normalization. So for what they mean population normalizing is kind of a normalization that based on the whole data set. It's like at the beginning, at the most beginning, people doing the deep learning work or machine learning work, they do not have much techniques. So what they do is just given the data, they normalize it. We don't want them to be spread out like most of them are just determining one bars, but we don't want some other distributions happened very large. So they just centering them or standardize them or a more advanced way is whitening. So, but this one is different. But in our center, I assume people know whitening but I still explain whitening will try not only standardize each of the dimension, but also make each of the dimension to be uncorrelated to each other, which means the covariance to be zero, correlation is zero. So, but this one generally will based on a higher techniques like PCA stuff. So it's more computationally expensive, especially you have very high dimension stuff. But sometimes it will be very useful for certain tasks. Okay, the advantage. It will exploit the beneficial property of normalization in optimization. And some drawbacks is that the estimation is not accurate because when you have the other samples coming in, the whole distribution or the statistical features will change for the data set. And also the internal covariant shift, the distribution of activation varying with training progress. And it cannot be used cannot be used. Well, it's just its performance will be less effective because the normalization starts from the beginning of the training process. And also other functions. So people have some other application of normalization, like this localized normalization. So what is local contrast normalization? So local contrast normalization is like for this part is specific used for computer vision for image input. So it can consider a patch and kind of normalize on that specific patch. And I assume they probably have a multiple patch and they just normalize locally separately.
across the same patch in all images, or like like or within
for
the same?
this one, I think is just because for images has channels for RGB image, or they have probably have more channels.
Okay.
For this one, the first one, I think it's just for one channel.
So it's kind of like a median filter, or what? Like
Not a
median
filter.
your
I don't
local.
think it's filter. The patch is fixed. This patch normalized, and that they should not be overlapped. I think.
So like split your image in the grids and
I didn't check.
okay,
It's
okay.
a bit because
I don't know what they're doing exactly, so I don't remember seeing it.
yeah, and then the local response normalization is through the whole channel, all the channels, like in the batch, in the patch, and the divisive normalization. Okay, divisive normalization is more like a generalization of the local contrast normalization. So it's more like a fan transformation applied to them. Not exactly, but it will give you some width to the neighbors of the batch. Each of the pixels will have different width, so it's kind of a mimic when people looking at something would kind of focus on one point and its surroundings which different attentions. And also the local context normalization will include all the channels. It's all ABS should be, but
These techniques for pictures mostly.
yeah, pictures, yes. Yes, for the local normalization, for the advantage is the limit measured by for visual data specifically. And the advantage is training is somewhat stable due to backpropagation through normalization. Okay. And the vision contrast environment property benefits generalization since it's trying to mimic the people visualize stuff. So it's what we think is a more generalized to real life and limits specific for image data, but I don't think it's specific for image data. You have sequential data or something, you can still do the same thing. So just a single channel problem. But yeah, it's just a no channel stuff, but still can based on the data you have. And may change the representation ability and reduce the discriminated information. I think this is because of the patch thing, because when you normalize as local location, the two part because globally they have some features, but when you locally normalize them, the feature change. It will like for images probably can affect the contrast or lightness of it, and this is for the localized normalization. And this is one of the big thing. It's not big things. It's an idea of the paper trying to deliver. They're trying to consider a normalization process into the three part. First one is the normalization area partitioning. Is what it can. So what part of normalization you want to apply? So when you throw a data into the model, you have a multiple channel model can multi-sample and can have different batch size or just single sample batch. So which part you want to normalize through it? This is one of what they call NAP. It's one factor decide normalization. And the second one is operation, the operation. How you do the normalization? You want to zero score standardization or you want to widen it? This is what I know. Probably they have more other operations. And another thing is normalization and representation recovery. I'm not sure if these three definitions just comes from this paper or people already have this term of them. But for the normalization representation recovery, then there is mainly about you want how much tuning because like if you ever tuning of the when you're using PyTorch, if you tuning of the back norm, you can see there is a parameter of the file if you want to decide true or not. It will give a trainable parameter to the normalization process. So this kind of process, we're trying to recover the normalized data to the original one, because the parameters will be updating during the training. And they kind of consider there's three definitions as just as the coordinates. And this is one, the red dot is kind of one of the normalization methods. given batch norm as an idea, is the NAP is through the batch, and the NOP is just standard deviation, and NR is a fan transformation. You use it or not. Okay, here is a list of different kind of normalization area partitioning. Batch normalization, I think you all know them. I will not go through that. And for layer normalization is more like the mean and the variance are computed across all channels within a single sample. So instead of so when you have RGB data, you just compute normalizes through each of the channel, to normalize in that channel, and it just works well for RNN and transformers. That's what they told me. And instance normalization, mean and variance are computed independently for each channel or each sample. Yeah, for the layer normalization, it's still going through the batch, and for the instance normalization, it will directly through, like you have a batch of RGB data, it will go through one RGB will normalize itself, or red, blue, green will normalize itself, and through all of the samples, it will normalize it themselves independently. This is what the group normalization mean.
So I have a question: how does it work? Are they using some function that learns how to normalize?
You can do that. It depends on work. If you want, I don't know if there is a PyTorch function of group normalizer, but it's
No, but there is a trick. I mean, there is no function in advance. It's just, hey, normalize, subtract the mean, divide by the variance. But each of them, I think, I'm not sure, but yeah, each of them has a trick that you multiply it by by parameters that are one parameter per parameter, one additional parameter per parameter. Plus, you learn the shift. Plus, if your parameters is an n by n matrix, easy to standardize. Find the overall mean, subtract the mean, find the variance, divide by the variance. Now what they do, n by n, multiply by n learnable parameters, and add n by n learnable parameters. The multiply is the variance, learnable variance. The add, so you standardize, but then you give the model the chance to learn it back, but in the way the model needs it. By multiplying, you're getting the variances. By adding, you're getting the mean.
I'm not sure if I get in that because we are talking about instance normalization and activation normalization, right?
No, I'm talking about everything here. Every one of them.
I was thinking about instance normalization. Like how can you normalize each sample independently from the rest? I would think that I would use some learnable function for that.
No, just compute the mean, compute the variance, subtract the mean, divide by the variance.
So in the normalization that the standard deviation here in the PyTorch, you can set there will be parameter here. You can set you use it or not. So it's will training, and during the exercise it will, it's a trainable, it will learn that parameter. If you want you can change it back, because currently it's standardized. But if you want to learn it back, you can set it be trainable. This what you're trying to mean to recovery.
What is it individual mean for each sample?
Depends. You can't say each time or each channel or each batch. It depends on what kind of normalization.
No, but I think confusion is Pavel is meaning something else by sample. So sample is a brain image, which is 256 cube voxels. You can compute the mean value of those voxels, and you can compute the variance of this value of those voxels, and that's what you normalize. Or you have an activation output of a layer is 10,048.
What?
By the batch size, if you flatten it. Or you have 10,048 per channel. So take 10,048 values, compute the mean, subtract it, or compute the variance, subtract. You have 10,044, 48 values for each sample, each channel. That's what you can compute the statistics over. You don't need other samples. Yeah, the only thing that goes across other samples is batch norm. And also it only does that within the batch. I think the I don't know, batch group normalization.
Yeah,
Maybe that's funky.
it's just a big idea. What Dr. Lee said is probably just a part of it. It's just give you this thing. You want normalize here or there, how you normalize it, and how you combine them. There's a trick. There's a trick you need to think of when you're training. So it's trying to deliver this information. This just leaves the part of them. When I'm reading their document, they try and keep declining that what we say is just a part of something, part of something. So there should be a lot of others.
No, but look, this is a good collection of what you can do, but they're all kind of the same. It's just changing where you normalize.
It will be different. So like you normalize the before or after activation. It's totally different. I think
No,
it can be totally different.
It's different in the same way that cooking in a different way is different.
yeah.
Yes.
It's kind of the same conception.
Yeah, does anyone actually buy internal covariance shift for a batch norm? Do you buy it?
No.
Yeah. That's the theoretical justification for batch norm.
No, but it was reanalyzed and kind of debunked or like explained.
Oh, really?
Yeah,
Unfortunately.
back then at the time.
Yeah. When Christian came out with it, he justified it with it combines internal covariance shifts of the different samples. Normalizes the trimming process, blah 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 blah. That's not even true.
Yeah, well, but the same for resonate. People are still talking about the residual stream, and I'm like, no, it's like you get it reverse. It's all about gradients flowing backwards. It's not about any residual stream and stuff. No, but like the people keep talking, and
I wonder how much confusion in the theory of this field is just due to the fact that people have no idea what they're doing and they're just calling for functions.
Yeah. That's in part of it, but also in part of that, we're taking names that are deliberately ambiguous, and then everyone is using them slightly differently. And we're still noting like, yeah, makes sense.
I still hate the name root norm, by the way.
Yeah.
That was terrible.
Well, I don't know what we're doing. Like after sessions with LLM, I decided like, let's just like forget about all of that. It's just because it's not this, it's not that. Simple Z scoring is just But we'll see what we use. Hopefully we can do that.
Hopefully, yes.
I think no, we're good. This was the information when I reading this paper, also trying to collect.
It seems like ad hoc. So
yes, everything
we know
we know everything, but we just sometimes we forget something. The NOP. So what is NOP? The normalization operation. So what kind of operation you are trying to do? So they just list the standardization whitening. Standardization we know zeros just a normalization or standardization, and the whitening process would be it's a little tricky. Is that you're trying to find that their eigen directions and project it to the maximum eigen directions is for the PCA. Then in that condition, you can say the difference between standardization and the whitening precise. When trying to standardize, it will just kind of stretch it a little or compress it a little, and still keep most of their statistic relations. But when you do whitening, it will, especially PCA, it will not only compress or stretch, it will also rotate it. So rotate it a little bit. But there comes out a problem. So what kind of whitening you use? They mentioned about that if you apply PCA whitening, this not work.
I mean, it's expensive, but why wouldn't it work?
Because we'll rotate. So they prefer. So this I think they're not trying to say not work. It's maybe just a bad worse than BCA. ZCA is zero fixed principal component. All I know is that the ZC will keep, it will not rotate it, will keep the ambient direction as what it is. So, but like there's two, like when you do pieces, will when you make it like Gaussian, will also rotate it a little bit, and this axis will change. And when you try to train neural networks, if you apply pieces through each of the layers, then there can be some problem.
So you rotate, widen, and rotate back. That's what they're doing. ZCA. Look,
Okay, I don't.
Well, but that's
Yeah,
what
okay,
that's
yeah.
what is written.
I didn't check. Unfortunately, just
Yeah.
okay.
Like look at PCA. You rotate and widen.
Okay.
And
so-
there you rotate Z transpose.
Oh, there.
Widen and then rotate back.
This is one more step.
Yeah. Well, I mean, you can. Well, exactly. You have to compute it.
Yeah, but still expensive. Yeah, this PCA costs the gas state swapping, and VC will rotate it back. That's it. And for the widening precise, okay, this is comparing widening with standardization. So it has a better conditioning theoretically. So it's the condition will back to the Hansen matrices. So when you have a landscape like the circle, the Hansen, the curvature will be more, I would say, more smooth, or and there will be no directional gradient will dominate the whole optimization precise, and can be better generalization. And some disadvantages is a computational cost. This is what we know. And numerical instability. I didn't check this part, but the Cholesky decomposition.
Well, I mean, the blue arrows probably offer a solution. Like what can we do to solve it? To make it more stable,
yeah.
to make it more.
Is a disadvantage.
Cholesky's decomposition is a little more stable, but than SVT say, but
Yeah, and it's more difficult to ensure the training and inference consistency. I think it's more like after training a model, we'll input the new data. So widening, I'm not sure it will affect the inference part.
yeah, but because it's too expensive, nobody does that.
Yeah, after expensive, then that.
Yeah, it's like the Peter lesson back again. Do something inexpensive, but do a lot of it.
Yeah, I'm trying to use my laptop run all the IC stuff. It's back to PC. I cannot do.
Yeah, PCA is good when you need to preserve variance.
And normalization representation. Oh, so actually, I also didn't read the following four. I just know about the fan transformation. This was just
Well, everyone does that, and it's hidden cost, right? You're increasing the number of parameters by 2, not by 2, by 3. So you have gamma and beta. So if you had k parameters, you will have 3k parameters when you do that, because you multiply each one by additional parameter. That's the gamma, each parameter, and you add additional parameter beta. So there's a like when it's similarly when you're talking about Adam and stuff like that. Those optimizers, they have a lot of parameters that they're tracking additional. Yeah, it's linear, but it's linear when you have a large scale model. Training 3 models at once. So
when we use Atom to train it, do people still use the scheduler?
yeah, I do. Yeah, still do use scheduler. Adam is there just stabilize the training. But as Mike showed in last talk, if you Adam also is poor at when you start with some steganography in your weights, some kind of setting, it just keeps it. But when you burn like with the learning rate scheduler, when you put the rate very high, when you push it, yeah, there is an opportunity to escape this kind of initialization.
And okay, I wouldn't talk much on fathers. I don't know exactly what they are, but give you the information instead of the fan transformation. You can do also the adaptive instance normalization.
Oh, but this
So
is for Pavel, right? Attentive normalization uses attention mechanism to control normalization adaptive. You were asking, so the one before last.
Is it working?
Okay, let's
Next. Okay, so for the NR normalization representation recovery. So what they do is for generally NOP, the operation part, we're trying to remove statistics. It can be standardization or lightning. You can see the images are removed by the lightness or their contrast. So what NR doing during the training will it's sometimes trying to recover to the original distribution. Like the first one also is already distorted, but it still looks similar to the bridge. But when sometimes when other NR applied, the people are trying to recover to some different distributions. It depends on still depends on what kind of task you're trying to achieve. So just here, give an example of how the NR works. So the next part is multi-mode. Okay, the multi-mode normalization. So sometimes when you have the data, they kind of come from different distributions or different modalities. It could be because it can be they do not share the mean or all the statistic parameters. So in this condition, people can try to train it to which here to give
that could be related to your John's or
yeah, the kind of
the holographic fusion. Okay, go.
I don't know. The kind of gated functions, and they're trying to normalize it through each of their gates and some combine them together. Some things.
Oh, so they're calling gating functions normalization, or it's separate. So
It's a separate. They will because they're coming from different distributions. They're trying to project it to, and therefore like a separate mode, what they call, and normalization for each of the gates output. Yeah. Also, notice. Yeah, it's just a normalization through of each of the learned gate result, and then add them back and trying to then another reconstruction back to the original statistics. And another interesting normalization trick is people have invented a method that you can pick which kind of normalization or what you can use. Okay, I can release the reference here. But what they do is no matter it's batch norm, layer norm, or instance norm, or you want to batch buttoning or instance buttoning, there's some algorithm help you to choose that, which I just feel is interesting. I'm not so sure it's cool or not because it definitely consumes a lot of computation, but there will be this kind of methods to do that. And if you're interested, you can checking on this, which will.
but this is like a universal solution. There is even a joke if in doubt, ensemble. Like XG boost and all of that. Is it just like that? Like just like okay, just ensemble everything. We don't know what works because it's a. But Mike, it wouldn't work in the kitchen though. It's like what? Sugar, pepper, salt.
Yeah, sugar and MSG is just the right way. It's the same thing as salt. So
This is only good for people who don't know how.
Okay, don't offer me your cookie. But yeah.
Okay, there's normalizing weights. This one So instead of you normalizing to activation normalizing of each layers, and there's another choice is doing concentrate on their weights. So like you can assume the transformation to be orthogonal, which I have some experience on that. So like when you're doing ISA, like especially for fast ISA, we know that the model will optimizing the transformation in a orthogonal way because what orthogonal doing is it will just rotate the input. It will not change their statistical relations. So when you get a zero mean and union variance, so which means your samples are already standardized. So if you fit it for a orthogonal transformation, all these statistic features won't change. It will just rotate it. It's more specific, like working on higher order statistic features. But it will keep the standardized things. There's the one they mentioned about normalizing width, and people doing that. Next off is normalizing gradients. This part I didn't go deep into that, but the ideas are still very same. They still consider like the gradients in the maybe some layer wise. Yes, you cannot throw back or throw layer or throw something how to you. I mean, it's just this something become the gradients of the data or width. Just still for information to check if you need it. I won't go so far if people want to discuss.
What is LAM? Layer-wise adaptive.
I don't know. I need to control that.
Okay, okay. It's fine.
Okay, oh, there's one other part. Okay, the next part is of the normalization and analysis. So they're trying to explain. So okay.
Oh, now the commandage. No, the explanation of why it works.
I think so, but I think we have already explained that. But let's go through this. Okay. And for the representation part, the fraction normalization is the most straightforward functions to control the distribution. As we see the zero mean, one standard deviation, one, and by adding the normalization to make the standardization to make the training more stable and controllable. And that's just what I think what they mean the representation is for each of the layer. They do not very dominate the statistic features. Like there's I don't want some of the neural has like 1,000 variance, but the other one has 0.1 variance. That will not make sense. That's what I think that's what they mean representation. And the optimization is about the Hansen matrix as the curvature or the gradient part we mentioned. They don't want the gradient to be dominated by specific directions, and this can be make the training more stable and fast. And the generalization is still all the same thing. And also, okay, one thing to mention about why we need it is about the scale environment. So you can see that when you're training neural networks, for the first layer, when you have weight W, and all the way down when you do back propagation from all the way down to your objective here. The first one, if it has a significant large or significant small value, it will cause what we know that is explode or vanish problem. We don't want that these things happen. So by standardized, no matter if you're in your standardized or in activation or standardized widths, it will keep the statistic features. This is how it's trying to control the gradient explosion or vanish problem. The math looks math, but it's easy to check. But just if you're interested, just check it. But it's that's what the idea I just mentioned. Is stable environment, and it can improve conditioning. So for the axis of this one is I remember it's a Hansen matrix, eigenvalue of the Hansen matrix, and the y-axis is eigenvalue density. I'm not sure exactly what the density. I assume it's just a strong. Oh, density.
Oh, maybe across layers,
yeah,
across many trainings or something.
In the back or the layers. Yeah, and you can see that the one with batch normalization, there's only the tail is very short, and it's kind of getting steady here. But without batch normalization, you can see the eigenvalue, the Hansen matrix, all the way down. They have like 2 times more than with batch normalization. So we don't want the Hansen to have so much spread out to the training space. And stochasticity. Yeah. So I think what it means, here is still when you have the data, when we say the back or more like where you want to normalize it, you have this part normalize it and that part normalize it. But when you normalize it all the way straight into the center, so the feature representation will change. It will increase the stochastic or more make the training percent more randomized. And I think this performance is mainly what they call they introduce the noise and make the model training more robust because the more stochastic precise. Yeah, I think this is the idea. And also another the last thing is batch size selection. So when you do batch, I think all of this is based on batch normalization. So when the batch size is small, like you have just 16, you can see that I think it's more the blue dots is more like normalize the points. So when I it means when they combine with some batch with the point where the points comes to like the red point is what we picked and it can be connected if this batch connected with that part the normalized one we're probably going to here but when there is more batch size like equal to 64 it will be more concentrate to the area so the this page would want to say is larger batch size can make it more stable, I think. Yeah, okay.
Thanks, Yaorong. Questions?
Can you go back one slide? One. So what does this picture show? That after normalization, the eigenvalues of the face got smaller.
Not smaller. It's eigenvalue. So yeah, they want also this related to the condition number. The condition number is the maximum eigenvalue. Yeah, they want it to not be that high because this is related to the smoothness of the gradient.
And so we can conclude that normalization is helping with that.
Yes, the batch model specifically. This.
Does this did you because I came in a bit late, not a bit, a lot late. Do you also talk about normalization in time series data? Did you say anything about
just the normalization? It can be anything. Yes.
Okay, it can be anything. All right. So in a case where you have the variance of the data is changing with time, right? The variance itself, or the mean in the variance, like in non-stationary signals, it happens all the time. Finance, fMRI, robotics, everywhere. the variance might be changing. I think it's called Hedgewood's cut. It's something. There's a word.
Heterosadastic.
Yes, that. Yes, thank you. Stochastic or whatever. Yeah. So, do you talk about how to normalize? What do you think about? Did they mention anything about that at all in the paper?
But this is not normalizing the entire data set. You're just normalizing the input sample, right?
Right, but the input sample can be the full time series. No.
Yeah, it could be. But this all of those methods kind of ignore that. But if you have a parameter per time point,
Mhm.
then this affine transformation could learn to take care of that. If you have stable low variance in one region and high variance in another, it will learn
Okay.
to normalize because you be multiplying. Yeah,
Right.
yeah,
Okay.
but it could be numerically unstable to if you have like very low values in the minus tens and very high values in plus tens and your first zero mean,
Mhm.
there's very low values
Yeah.
will
Okay.
disappear because and then you multiply,
Right.
they become a bit smaller.
You become this. Heterosadasticity. Skedasticity. Yeah. Word.
Yeah, that's very interesting.
What is
Things.
different to stochastic T and random
Stochasticity.
language question?
No, I mean,
Stochasticity is when you want to be Greek.
yeah, it's kind of the same word. Yeah, but no, it's different context, different flavors. Random is this is random. Stochastic, specifically about processes, about like it's different context. It's like any words you have 15 synonyms for the same thing, but they seem to be the same at superficial level, but the context that they're used in is different, so that gives you some differentiation.
So what is the main problem, I guess, that Backstrom is trying to solve? Because it feels like there's a lot of things that are conflated in this paper, and it feels like maybe some of it's kind of like tangential to what Mike talked about with like muon and stuff like that. But so we're mainly trying to scale the activations throughout the network or weights with batch norm.
Batch. Sorry, I didn't get. I think what you're asking is what the batch norm will. I'm
Yeah, I
sorry.
guess like what is the main motivation for batch norm? Is it because like
I want the paper. So batch normal from this paper, they're trying to state this is I think we can make sense here. Is that batch norm is just an activation to some extent, and it will add into each layer, and they are keeping the batches statistic features. Because when training the weights, you normalize weight is another trick. But for batch normal specifically, when you training the model, sometimes you based on the objective you chosen, the weights can or the activation can go up or go down, big or small. So the gradient will explode or vanish. Rational would solve this problem. And but yeah, thinking you're not asking it. But batch norm is specifically through the batch.
I guess like what problem is batch norm trying to solve? Only vanishing and exploding gradients, right? But there could be multiple causes for them. I guess. I don't know. It seems like there's
It's the easiest voltage solution to the constraint of after computing a batch, we have the sum of the gradients. If you don't normalize along the batch dimension, then variances between samples in the same batch might throw off the gradient if you sum it up. But if you do normalize for the whole batch, then when you sum up the whole gradient, you have predictable behavior for how that sum works because everything is pre-normalized.
More important for training or
Yeah, it's only for training. I think it's pretty much useless to use it in like a regular statistical context. It only makes sense.
where you can improve the generalizability since you normalize and stuff.
Maybe not directly, right?
Not directly, I don't think so, because it doesn't impact the operators who use it. Only impacts the only thing it actually touches. It doesn't even touch the operator. It only touches it touches a back prop. The only place where the batches interact is in the back prop. The operator does not care that you're operating over a batch.
Well, batch norm is over a batch. And
Yeah. But the only thing else that touches the batch dimension is the sum when you're doing autograph.
Or otherwise, then you have different weights essentially, right, for each cup.
Yeah,
Which is
yeah.
weird. Which you
No,
can't
the
really
weights are,
use.
well, you have, in a batch, you have credit per sample. And you're just taking average of that credit.
Yes.
Exactly.
So you want the scale of those credits
To be
to be
Comparable,
comparable.
right? So,
Mhm.
yes.
That's all.
Because I don't know if it would actually impact the operations of the models actually do. I think it only impacts the learning dynamics of the model.
Well, I mean, I would assume that it does, but just not direct.
Yeah, like the second order thing.
But it also, any normalization, not just in deep learning, it is about what we're interested in the data. Does scale matter or variations matter? If variations is the only thing that we care about, then why keep scale there? Let's just get rid of scale so it's easier downstream to focus on the important stuff. So it's things like that. But there is a dogma in deep learning that just sort of figure it out.
Oh, yeah.
It doesn't match that dogma.
Okay.
It's just like,
Oh, yeah.
but it will not figure it out. You have to know what you're doing. Okay. Sounds good. Let's stop the recording here. Thanks for everyone who connected online.